Welcome back to Integral Calculus. In this video, I want to talk about the catenary arc. A catenary arc is a very fundamental shape in the study of physics and material science. It is the shape that you get if you take a piece of flexible rope and hold it on either side in such a way that it is allowed to pivot. Right, if you hold the rope tightly, you'll notice right near my fingers it kind of moves this horizontal way. We want to ignore that part and just consider the part that's going down, kind of making a loop and coming back. If we pull those two ends a little bit further apart so that there is less rope, then we get a longer, shallower one. If we bring those two ends closer together, we get a shorter, skinnier one. There comes a point where the physical nature of the particular rope that you are holding prevents it from getting exactly as flexible as it ought to be. But that shape is known as a catenary arc. It is not a parabola, as many people want to believe. It is a much more complicated shape. I'm not going to get into the physics of how and why we discovered that this is the way that the shape works, because, well, I don't really care. This is math class, not physics class. If you're really curious, that information is available elsewhere on the internet. Instead, I want to look at the mathematics behind this, starting with the equation for the catenary arc. Y equals A times the cosh of x over A minus A. I want to point out before I do anything else that the minus A right here is actually arbitrary. That allows us to define the arc in however we would like. But specifically, subtracting A is going to force the minimum of the curve to be at the point 0, 0. We know just from our brief introduction that the catenary arc is going to have a symmetric appearance, and it is going to have a minimum at the center. The point of minus A is to put that at 0, 0. Before I do anything else, I want to verify a couple of things. Is the minimum actually at x equals 0? Or is there another point in xy space that would be better served as the minimum? Is 0, 0 actually a point on the curve? That's perhaps the easiest thing to look at. And I guess 3, is the curve symmetric? Those are the 3 claims that I made about the curve that are well within the scope of this course to investigate. Let's start with the easy one. Is 0, 0 a point on the curve? Well, if we take A times the cosh of 0 over A minus A. If we know what cosh of 0 is, this is fairly easy. I might break off to the side and simply look at cosh of 0. From the basic definition, that's going to be e to the 0 plus e to the minus 0 all over 2. E to the 0 is 1. E to the minus 0 is also 1. 1 plus 1 is 2. 2 divided by 2 is 1. So this is going to be A times 1 minus A, which is just A minus A, which is in fact 0. So 0, 0 is a point on the curve. You plug in x equals 0, you get out y equals 0. Is the curve symmetric? Well, mathematically, when we talk about whether something is symmetric or not, we're generally thinking about even functions. So if I take a times cosh of minus x over a minus a, well, let's come off to the side this time and look at what happens in cosh of minus x. Well, cosh of minus x would be e to the minus x plus e to the minus x, which is just e to the x, all over 2. And that has just changed the order of addition, but addition is commutative, so we can equally easily write this as e to the x plus e to the minus x over 2, which is just cosh of x. So cosh of x itself is an even function, which means that when I put the negative here inside of cosh of x, it doesn't do anything. So a times the cosh of minus x over a minus a is the same thing as a times the cosh of x over a minus a. We know that this function is even. I guess all that leaves is the question of a minimum. It's been a while since you've thought about extrema on a curve, but let's take a minute and think about that. If I have the function f of x is a times cosh of x over a minus a. Well, to find extrema, we usually look at the first derivative test. So f prime of x will be a times the derivative of cosh is sinh of x over a multiplied by the derivative of the argument. The derivative of x over a is 1 over a, and then minus the derivative of a. A is a constant in this expression, so that's not doing anything, and that's the whole thing. The a and the 1 over a are going to cancel each other out. So we're left with sinh of x over a. Critical points occur when this derivative is equal to 0. Trying to figure out when sinh is equal to 0 is a little bit tricky. I think I'm going to go to the exponential form. So this is e to the x over a minus e to the minus x over a all over 2. Multiply both sides of the equation by 2. And add the negative 1 to both sides of the equation. E to the x over a is equal to e to the minus x over a. The exponential function is a monotone function. It's 1 to 1, always increasing or always decreasing depending on whether the argument is positive or negative. But importantly here, it has an inverse that's valid everywhere. So if e to the x over a is equal to e to the minus x over a, that can only be true if the exponents themselves, x over a, is equal to minus x over a. Multiply both sides of the equation by a. X equals the opposite of x, which you probably know only happens at one point, but to be technically correct, add x to both sides of the equation. 2x equals 0, and divide by 2, x equals 0. So there is exactly one extreme value on this curve. It occurs when x is equal to 0. It could be a maximum, it could be a minimum. And this is actually the place where I have to jump in and say, well, that's good enough, because we have a coefficient in the front of our expression. The a that we chose is arbitrary. Depending on whether a is positive or negative, this could be a maximum or a minimum. We have to use the physical argument of, I know that this is a curve that goes downward, to say that we want a positive value of a, which will give us a minimum. If we had a negative value of a, that would give us a maximum. And that is something that can and will exist in certain applications. Most famously, the St. Louis arc is a catenary arc that is a giant monument curved upward. So that has a maximum at x equals 0, not a minimum. A little bit disappointing to have to end with a physical argument, but I guess that counts for something. There are a couple of different ways that you could test this otherwise. Probably what I would have done is continued on to the second derivative test. Take the derivative of sinh of x over a, you get 1 over a times cosh of x over a, and see what happens if you plug in x equals 0, you get 1 over a, which again is either positive or negative depending on whether a is positive or negative. If the second derivative gives you a positive value, that means that the curve is concave up, and when the curve is concave up, it must have a minimum. If the second derivative is negative, that means that the curve is concave down, and when the curve is concave down, you have a maximum. And that's actually enough for us to wrap up here. I could continue playing around with how to graph this by hand, but instead I am going to jump into Desmos, where I have already programmed this in. So we have a times the cosh of x over a minus a. I have a slider so I can change values of a. You can see that for larger values of a, we have the curve spread a little bit further apart, so it becomes a shallower curve. For smaller values of a, get down, we get the curve pinching a little bit closer together so that you have the endpoints held closer together and it is a deeper curve. And if I swing all the way down to negative values of a, you can see that the whole thing turns upside down. All right, so that's the basics of where I'm looking here. And once again, the choice of subtract a very specifically is setting the lowest point on the curve at y equals 0, so that our measurements are how high are things compared to the lowest possible value. If we had a different condition, we might want to add or subtract further from this. For example, if we knew that at x equals 5 and at x equals negative 5, our catenary was suspended from poles that were 12 feet tall, we might want to use those and shift things up or down. That would allow us to more easily calculate what is the height above the ground of that minimum value. But those sorts of considerations are, again, beyond the scope of this course. Instead, let's get back to my notes sheet. I want to find the length of rope necessary to form a catenary, which follows the curve y equals 3 times the cosh of x over 3 minus 3. So it's the basic form of a catenary, plugging in a equals 3. And we know that it's pinned at y equals. We know that it's pinned at x equals 5 and at x equals negative 5. So again, a practical application here might be something like you have utility poles placed 10 yards, I guess, apart. So we'll call that x equals positive 5 yards and x equals negative 5 yards. And we know that we want the curve to hold this sort of form because that's going to give us the kind of arch that we need for the stability of the poles. I don't know if that actually makes sense in the particular numbers that I gave here, but that's the sort of thing that we're looking at. And with that information, how much of the power line is actually strung between those two posts in order to give us the nice smooth curve we're looking for. All right. So this problem is asking about arc length. It's been a while since we've talked about that, but I'll remind you that arc length is the integral from a to b of the square root of 1 plus f prime of x squared dx. In this particular case, we have that f of x is 3 times the cosh of x over 3 minus 3, which means that f prime of x is going to be the sinh of x over 3. F prime of x squared would be sinh squared of x over 3. And we get that s is going to be the integral. Our endpoints here are negative 5 and positive 5. We have the square root of 1 plus sinh squared of x over 3 dx. This video is getting long enough, so rather than try to give you a problem to try on your own, I'm going to make you finish this. I've done all of the setup, gotten us to an integral that we can evaluate, and I would like you to see if you can figure out how to do the evaluation. I will give you the hint that if you remember the Pythagorean-looking identities for the hyperbolic functions, this integral simplifies very nicely, and you can finish from there without too much issue. If you give me an exact value, just involving sinh or cosh of numbers, that's good enough. I will also do a decimal approximation because I think that sort of thing is interesting for this particular type of problem. But take a couple of minutes, see what you can do with that, and I'll see you in the next video.